Good morning. I want to give a presentation. The title is shown like this: the molecular imprinted polymer-coated AuNPs sensors for alpha-pinene vapor detection. Here is the outline is shown like this. First part, I will introduce the terrapin. In this research, I just introduced alpha-pinene detection. The second part is I will introduce the principle used in this research, localize the surface plasma renaissance mechanism in AuNPs. Third one will be the experimental part, and fourth one is a schematic graph of the MIP AuNPs substrate. The fifth part will be result and discussion part. The next one will be conclusion. First, I will introduce a terrapin introduction. Terrapin is a large and diverse class of organic compounds. It's produced by a variety of plants at the growth state, biomarkers, and derived from isoprene, and the basic molecular formula is shown like this. And it have a strong smelling and protection. It have a protective functions. In the normal process, plant will emit a lot of kind of vapors. But in some herbivore conditions, the emitting amount of terpenes and their derivatives will increase a lot. So that is a interesting part in our research. And then this is the localized surface plasma renaissance in AuNPs. It's shown like this one. When there are some gas vapors generated in the around the AuNPs sensors, the environmental refractive index of AuNPs will be changed. So here, the delta lambda sheet will be changed. So detecting this part, we can think that there are some gases generated around the AuNPs. And the advantage of this kind of sensors is the short response time, its real-time detection, easy fabrication, and better repeatability, and also can avoiding the wiring system, which is easy to induce inference. And in this research, the molecular imprinted polymer-coated AuNPs sensors shown like this one. Template here, we use Alpha-Pinenes, monomer cross imprinted polymer initiator is shown like this one. And theoretically, these Alpha-Pinene vapors will be entrapped in the thin molecular on AuNPs shown like this one. And first, in order to verify whether there are some MIP effect in the powder, we make the experiment shown like this one. First, the polymerize in the water base at 6 centigrade for 6 hours and grind the bulk polymer solid into powder, and then heat it at 16 centigrade to evaporate all the target vapors, and then input it into this kind of equipment for the absorption experiment. Last part will be the GC-MS instrumental analysis process. And this is absorptibility compared with this NIP and MIP powders. It's shown like this one. Well, here we can see that the absorption ability of MIP powder is higher than NIP powders. And also here we use a constant K, which equal to like this. And we thought that when the K is lower than 1, that means it's low affinity. And then if K equals to 1, there means no selectivity. If K is larger than 1, that means the selectivity is generated here. And also from this graph, we see that the tiny vapor imprinted polymer have a certain selectivity generated in the imprinting process. And also then according to the result, we made the polymer films on glass substrate. And then we use the different molar ratio of template alpha-pinene to monomers and compared with NIPs. And here, the molar ratio 1 to 4 is the best absorption ability. And also we compare the K value, the 1 to 4 molar ratio of template to monomer show the best selectivity result. And then this is a schematic diagram of the MIP AuNPs substrate shown like this one. And the practical structure is shown like this. The size of the AuNPs is thought to be about 13 nanometers, and the polymer thickness is less than 10 nanometers. And then we detected the spectrum of spin coating the polymer AuNPs films with different spin coating speed, shown like this one. the polymer layer made the plasma absorption peak lambda shifted to the red and the transmittance decrease. The increase of spin coating speed made the plasma absorption peak lambda shifted to the blue and the transmittance increase. And we use a ellipsometer to verify the dependence of polymer thickness on the spin coating speed. Here, the AU substrate is shown like this. AU layer is 200 nanometers, and then we drip the same amount of polymer liquid and with different spin coating speed. The thickness value is shown like this one. So the polymer layer on AU nanoparticles should also follow the same trend. And also we investigated the surface morphology of NIP-coated AU nanoparticle film. And here the roughness value of AET and NIP-coated AU nanoparticle substrate the roughness value are 1.8, 1.3, and 2 nanometers respectively. This result is also in constant with dependence of polymer thickness, which detected using the ellipsometer. And then last part, we detected the refractive index sensitivity of NIP and MIP-coated AU nanoparticle sensors. Here, there will be some transmit light using the UV-1008. And then where there are some gas molecules generated around AU nanoparticle substrate, there will be some decrease in transmittance. We defined it as delta T, and some lambda peak redshift, we defined it at delta lambda. And we investigated this sensitivity we defined here with different spin coating speed to the same concentration of Alpha-Pinene wipers. And the result is shown like here. Here that when the spin coating speed is nearly 1,400 nanometers, the NIP and MIP result is better separated, and the sensitivity of MIP is better than NIP. So here we think that the optimum spin coating speed. From this result, we gain that the thickness control of MIP layer could realize the sensitive and selective Alpha-Pinene detection. And also we detected the real-time response characters of this AU nanoparticle, MIP-coated AU nanoparticle substrate. The real-time response character was detected as a single point transmittance at lambda equals to 562 nanometers, and the real-time responsible time T17 here is less than 3 seconds. And here the response of the refractive index change is rapid, reversible, and reproducible. Even though there are some MIP layer on the AU nanoparticles, there is no so much effect to the sensing speed. And then the conclusion part will be, firstly, Alpha-Pinene detection was realized by the molecular imprinted polymer-coated AU nanoparticle sensors. Secondly, the real-time response of MIP-coated AU nanoparticle sensors was approved to be rapid, fast, and reproducible. Per se, that means in the future research, we want to make more kinds of terpene-imprinted MIP powder and films, and then compare their absorption result. Here we want to thank for the Strategic Information and Communication R&D promotion programs for their financial support. This is all the content of my presentation. Thank you for your attention.